So as we continue talking about Lewis structures and all the ins and outs of Lewis structures, we've talked about how to draw them. We've talked about how to determine what shape they are and what bond angle you're going to get. And today it's time to talk about how to know if they're polar or non-polar. So we've talked about two different models of electron distribution prior to now. Long ago, we talked about oxidation number. When we talked about oxidation number, we said it's like the electrons are being completely transferred. We didn't use these words, but completely transferred to the more electronegative atom. Now that we know what electronegativity is, that makes more sense. But the electrons are being completely transferred to the more electronegative atom. So even though we've said these are making a bond and they're shared, if you assigned the formal charge, if you assigned the oxidation number of F has a rule of always being -1. H has a rule of almost always being +1. So H is +1, F is -1. That's complete transference of electrons. It's pretending that those two electrons are not shared whatsoever between the H and the F. The other model of electron distribution is formal charge. This is still new to us, but formal charge says the electrons are shared completely equally. So we would say F is in group 7, and in this molecule he's got 6 as a lone pair, he's making one bond, he has a formal charge of 0. Hydrogen's in group 1, and he's making one bond, he has a formal charge of 0. We would say both of those have a formal charge of 0. So completely transferred in oxidation number, completely shared equally in formal charge. These are the two extremes of what Mother Nature does. These are the two extremes that are probably not accurate for most of the molecules that we will talk about. There's usually partial sharing of electrons. Fluorine is more electronegative than hydrogen. So because of fluorine being more electronegative than hydrogen, it's more selfish. So there's more buildup of electron density around the fluorine, less buildup of electron density around the hydrogen. The way we show that is by this thing called a dipole. This is a dipole. A dipole has a plus-ish end on the butt of the arrow, and then an arrowhead. The arrowhead is always pointed toward the more electronegative atom, and the plus butt end is on the less electronegative atom. So the dipole in HF points toward the fluorine because fluorine is more electronegative than hydrogen. What that really indicates by that dipole is there's partial sharing of electrons. It's not a +1, it's not a 0, it's somewhere in between. It's not a -1, it's not a 0, it's somewhere in between. These actual dipole numbers are not something we expect you to know, but knowing which direction the dipole is pointed is absolutely something we expect you to know. So, because this molecule has a dipole, we say this molecule is polar. We would call HF polar because there is a dipole. I'm going to say a little something that probably is getting ahead of myself a little bit, but when there is a dipole along bonds, you have to consider whether one dipole cancels out with another dipole. If all of the dipoles cancel, we would say that molecule is nonpolar. That's getting a little bit ahead of myself, but I said it anyway, and I'm not editing it out. So we said HF has a dipole. How did we know that it should have a dipole and not extreme no sharing? Well, it depends on the difference in electronegativity. If there's no difference in two atoms that are bonded together that are the same electronegativity, we're going to say that makes a covalent bond. An example of that is O2, Cl2, I2, H2, carbon-carbon bonds. Two things of the same type bonded to each other. So there's no difference in electronegativity when there are two things of the same type bonded together. When there's a greater than 2 difference in electronegativity, again, you don't have to remember numeric values of electronegativity. We've seen the trend on the periodic table. But if there's a big difference in the electronegativities of the atoms that are bonded, that actually makes an ionic bond, and MgO is an example of an ionic bond. If I look up the mathematical values of electronegativity, this is oxygen minus magnesium, that's greater than 2 difference. When do we expect to get a greater than 2 difference? Well, when you have a metal and a nonmetal. So metal and nonmetal, that's ionic because there's a greater than 2 electronegativity difference. What if you're greater than 0 but less than 2? That's where we have covalent bonds, but polar covalent bonds. Water is an example. Weirdest way to write water ever, I know. But water is an example of a polar covalent bond. There's our actual electronegativity difference, oxygen minus hydrogen. We can also talk about HF being a polar covalent bond. Covalent bonds share equally. Polar covalent share partially. Ionic share not at all. So this is shares most to shares least. That's in that order. That says shares, but it looks like something else. Who knows? Covalent, polar covalent, and ionic. So polar covalent is something that has a dipole in it, partial transfer of electrons. A dipole looks like this. Oh, yep, I didn't say this yet. The plus end of the arrow, the butt of the arrow, is said to have a partial charge. That's called a partial negative, partial positive, dang it. I don't even know if that's how you spell partial. Here's a partial negative. That delta, that's a lowercase Greek delta. Lowercase delta means partial charge. It's not a complete formal positive one or formal negative one. It's a partial charge. Anything that has a dipole has an unbalanced charge, we would call it polar. Anything that has a balanced charge, we would call it nonpolar. Behavior of polar molecules and nonpolar molecules are different. So if we say that we've got a whole bunch of polar molecules, what that means is we've got one end of the molecule that's partial negative, one end of the molecule that's partial positive. In all of these molecules, we have those little partial charges on them. So when you apply a charge to these outside plates, meaning put some plus charge on this plate, my molecules line up accordingly. So my molecule that's polar lines up with the negative end being attracted to the positive of the plate, pulling the positive end in towards solution, making a negative positive of the next molecule align, negative positive of the next molecule align, and again until you've got the positive of a molecule aligning with the negative of the plate over here. Behavior of polar molecules and nonpolar molecules is very different. We have different physical properties, as in boiling points and melting points and things like that. We will talk about that. But we also have like electric current properties like this that we can take advantage of in polar molecules. That's a wrap for this one.